Okay, this lesson today is going to be about sequences and series and how you decide whether they converge or not. And so if you notice that what I have on the screen is your handy dandy study sheet for series test. This is in your formulas for game day, and you have to have this memorized for option 3. There is no way around it. But what I'm going to do is kind of go through and give you an example of each test to kind of refresh your brain on all the different types. Okay, so first of all, just kind of going back to the basics, is what is the difference between a sequence and a series? So if you'll remember, a sequence is just a list of numbers. Okay, so it might be 1, 1/2, 1/4, 1/8, and so on, and that's a sequence. Okay, and so if we talk about whether a sequence converges, what we're talking about is, are these individual numbers heading towards one particular value? And so for this, if you notice, they are getting smaller and smaller and smaller as I go, and they are heading towards 0. So we're looking at, what do the individual numbers themselves go towards? Now I say that, we can recognize this easily as a geometric series, with the first term being equal to 1, and then the common ratio being 1/2. Okay, and we know that we do have our formula sheet for geometric series, and this isn't even a calculus topic. Okay, but we can just look and say this is the formula for the nth term of a geometric series. We have the sum of a geometric series that's finite, and then we also have the sum of an infinite geometric series, and this is right here under the algebra topic. So if you just look at u sub n, is u sub 1 r to the n minus 1, just the formula for an nth term. And then if you're looking at an infinite sum, which we're not looking at a sum here, we're looking at a sequence. Okay, we will need that formula later. And so when you look at this, we can write a formula for this particular sequence that I have, and that would be u sub 1, which is the first term, times the common ratio, what you're multiplying by each time, which is 1/2, to the n minus 1. So if you want to figure out if the sequence converges, you can just find the limit as n approaches infinity of whatever that sequence is. You're just trying to see, is that particular sequence going towards one particular value? And this one is going to 0, because we know that if you are geometric, with the absolute value of your common ratio being less than 1, the sequence does converge to 0. Now the other thing about this, if you're just looking at a sequence, you can graph it. You're guaranteed to have the graphing calculator on paper 3, so we could just graph the function. So we could graph 0.5 raised to the x minus 1, and we could just take a look at it. Okay, and visually this does appear to be going closer and closer to 0, and you are definitely going to have that on your test. So that's a sequence, but that's not what this big study sheet is all about. It's about series. Okay, but let me give you just one more. Just take a nice little one more sequence before we go. Okay, this is a sequence. We could graph it as well. Okay, we could just change it to x's. And we could graph x squared over 3x squared plus 1. So we could see what the individual numbers were doing as you go to infinity. Well, it seems to be flattening out here. Let's look at the table. Okay, so we're just looking from 1 on. Okay, so if you look at this, it starts, if you substituted 1 into the formula, and you kept going, just kind of take a look at this, it does seem, have a little bit of numerical evidence for this seeming to go towards a third. Okay, so you could go quite a ways out, but the general idea is it seems to be going towards a third. So for this particular sequence, if I was listing out the numbers, that table was actually listing out the sequence for you. You could substitute in 1, 2, 3 and get the values that they said. But you're just taking the limit as n approaches infinity to see if that sequence is converging. And if you'll remember your horizontal asymptote rules, if you look here, the degrees match, and so this is just going towards the leading coefficients, or 1/3. Okay, so this sequence converges to 1/3. Okay, so we don't tend to do too much with the sequences. What we spend the most of our time looking at is series. Okay, one more brief little thing I'll mention to you. If the limit as n approaches infinity of the absolute value of the sequence goes to 0, you do know that the limit as n approaches infinity of the sequence will go to 0. So if you happen to have something that's alternating, say it was the same thing up here and it just went at 1, -1/2, 1/4, -1/8. If you didn't want to check the alternating sequence, you could just check the absolute value of the sequence, and if that went to 0, then you would know that the sequence alternating also went to 0, so you can keep that in mind as well. Okay, so what we really want to get to, though, is the series test. And the series are just the same thing, only we're adding it. It's a sum. So the question becomes then, are the individual terms going towards one value? Are they going towards 0? But if you start adding all these, what are they going towards? And that's what our series tests are used for. Okay. Again, on this one, what we're talking about is just adding up all of these terms from 1 to infinity. It's the same formula as the one that I had up there before I was alternating the signs. Okay, this is the sequence that we are trying to sum. Okay, and so if you put in 1, that would be 1/2 to the 0. That gets you your first term, which is 1, then put in 2, and so forth. Okay, so this particular one we would recognize as a geometric series. If we're adding them, it's called a series, with r equal to 1/2. Now, that is one of the tests, even though you've known it since Algebra 2, for geometric series. Okay, if the absolute value of r is less than 1, it converges. If the absolute value of r is greater than or equal to 1, it diverges. And not only that, we can actually find the sum if it converges. And it's just the first term over 1 minus r. Now, you don't have to memorize that because, like I told you, you've got that under algebra if you just recognize it as a geometric sequence and thus a geometric series when you're adding it up. Okay, so when we look at this, that would be a test that we use, geometric. If you notice, you're multiplying by the same thing every time. And you'd say, okay, absolute value of r is less than 1, converges by the geometric series test. And not only that, you can find out what it converges to. Okay, so the sum to infinity is u sub 1 over 1 minus r. So the first term over 1 minus the common ratio, so 1 over 1/2, or just 2. Okay, so sometimes you just want to know if it converges or not, but if you wanted to know the sum in that particular instance, we can actually find the sum. Okay, so that's one of the tests that you can use. Okay. Here's another one. Let's say that I was trying to find the sum from n equals 1 to infinity of the other sequence that I was doing. Well, one of your tests, in fact the one that you should in general try first, is the nth term divergence test. Okay? So if you remember, the nth term divergence test is only a test of divergence. It won't tell you if it converges, but it will tell you about diverges. Okay? If the limit of the sequence is not 0, then the sum is absolutely not going to be 0. Okay, so in other words, if I take the limit as n approaches infinity of the sequence, just the individual numbers, we already said that each individual number was starting to head towards 1/3. Well, that's clearly not 0. Okay, so if the terms themselves aren't getting smaller and smaller and smaller, there's no way that the sum is going to approach a certain value. If they're all close to 1/3, you're just going to keep adding 1/3 every time, and you're not going to converge to one value. It's going to go to infinity. So your first line of defense is actually the nth term divergence test. Okay, so any particular series that they give you, if the sequence, that is the limit as n approaches infinity of the sequence, does not go to 0, then it absolutely diverges. Now, if it happened to go to 0, that tells you nothing. It may or may not converge. Okay, Okay, but if you get anything besides 0, you absolutely know it diverges and you don't have to do anything else. Okay, so far all we've done is talk about geometric and nth term. Okay, nth term is really what you should do absolutely first, because there's no way it converges if the sequence, the individual terms, aren't going to 0. Okay, geometric is one of our easiest ones. We've known that since Algebra 2. P-series is the next one I'm going to talk about. Okay, so you notice that it's in this form, so just a little example here. Okay, if we did the summation from n equals 1 to infinity of 1 over n squared, and they want to know if that converged or diverged. Okay, well, if you take a look, this looks like your P-series. Okay, and for me, 1 over n to the P is just 2. Okay. Well, if P is greater than 1, it converges. P is less than or equal to 1, then it diverges. Okay, so just make a little note. P greater than 1 converges. P less than or equal to 1 diverges. And if you'll remember, P equal to 1, we also call that the harmonic series, which is somewhat famous for diverging. Okay, so in this particular case, all we would have to do is say converges by the P-series test, P equal to 2. Okay, now really that's not difficult at all. Generally speaking, what we use the geometric and the P-series for are for our comparison tests. So these are very well-behaved functions. We know what they do. We understand their behavior very well. And we'll also compare other series to them, either using the comparison test or the limit comparison test. Okay, so very important to remember, P-series and geometric are most often used with the comparison, and that's sometimes called direct comparison as well, and limit comparison tests. So they are a useful tool for that. Okay. Alright, so the next test on our nice little list is the integral test. Okay. So I'm going to do an example of that one. So we have the summation of n equals 2 to infinity of 1 over n square root of ln over n. Now the first thing that you have to look at is this function something I can integrate? It's an integral test. Okay, but if you look at the function itself, in order to apply this test, you must have a positive continuous decreasing function. Now you can prove this a couple of ways. One is you can take the derivative and show that it's always positive. You could see if the next term is smaller than the previous term. You can also graph it. Okay? You're definitely going to have your calculator when you're on paper 3. So let's just take a look at what this guy looks like. Of x. Okay, this does appear to be positive, even though it's above the x-axis. It does appear to be a nice continuous decreasing function. And I'm not proving it, but I am giving it a check with my graphing calculator. I do have an asymptote there at 1, since ln of 1 would be 0, making the denominator 0. Okay, so what I'm going to do is I'm just going to put a little sketch here. Put a little asymptote at 1. And just do a little sketch. And I'm going to say that this is a positive continuous. I might have lost it on continuous there. Decreasing function. Okay, and at least for n greater than 1, or x greater than 1 if you're talking about the function itself. Okay, and so that means that I am allowed to apply the integral test. So if you look at the integral test, function has to be a continuous positive decreasing function. When you take the integral, if the integral converges, then the series also converges. If the integral diverges, then the series also diverges. This also tells us some information about the bounds. So notice on this one, if it converged, I could find the sum. On this one, I can't find the sum, but I can get it within a certain range. Okay. Now this does say to integrate from 1 to infinity, but since my series is starting at 2, I'm going to go from 2 to infinity. So I'm just going to find the integral from 2 to infinity of this function. And I'm going to go ahead and write it as ln of x to the 1/2, because it's kind of leaning towards power rule for me. Okay. Now one thing you have to know right off, you've got an infinite limit, so you're going to have to change this to the limit as b approaches infinity of the integral from 2 to b. And I'm also, while I'm at it, I'm going to bring this guy up, make it to the -1/2. Oh, I lost a dx over here, times 1 over x dx. Okay. All right. And so that's going to be what I'm trying to find. Well, this is just a simple u substitution. And so we're going to say u is equal to ln of x du, right there smiling at me. So, if I rewrote this, it would be the limit as b approaches infinity, the integral from 2 to b of u to the -1/2 du. Okay, now the bounds actually change when you do a u substitution, but we're going to go back to x's at the end, so we will be all right. Okay, so if you integrate this guy, add power rule, so add 1 to the exponent, be u to the 1/2, times the reciprocal, which is 2. And that's going to be from 2 to b. And then we would have the limit as b approaches infinity. Go ahead and substitute back in what your u was. Now we're accurate with our bounds, now that we're back to in terms of x's. And then we're going to substitute in our bounds. So we have the limit as b approaches infinity of 2 ln of b to the 1/2 minus 2 ln of 2 to the 1/2. Okay, so the key is always this part. This part's generally speaking always going to be a constant. You want to know what is happening to this as you go towards infinity. So if you think of, basically just graph it. It's probably the fastest way. Now, if you know how ln of x behaves, you probably know the square root is just a little bit muted compared to that, a little bit depressed compared to that. So I'm going to just do 2 times, I don't really need the 2 to know the behavior, but square root of ln of x. Okay, and this guy is clearly getting higher and higher, just like ln of x does. It has a slow rate of increasing, but it definitely is increasing. And so that guy is going to infinity. Okay. So what's happening is this part, as b goes to infinity, this is going to infinity. And then as b goes to infinity, that doesn't affect that at all. It's just a constant. And so this is infinity, which is diverging. Okay, so then you need to tell them, you know what's up. The integral diverges, therefore the series diverges by the integral test. Okay, we'll say a good signal that it might be the integral test. They tend to have ln in them. That's one of the common themes. Also, turning out to be an arctan at the end, because we know that arctan, as you go towards infinity, goes to pi over 2. That seems to be another favorite with integral tests in general. And just so you don't get bored, I got to throw in a Roger Dodger for my friend Jack Jolling. So Roger Dodger there on the integral test. Okay, and so now moving right along, I got a couple of tests to go here. Whew. We've made it through nth term, geometric, p-series, integral test, comparison and limit comparison. Okay, for comparison tests, basically if you're smaller than something that converges, you're going to converge too. If you're larger than something that diverges, you're going to diverge as well. Okay, so that's fair enough. If you are smaller than something that diverges, you don't know what's up. Okay, if you're bigger than something that converges, you don't know what's up. Okay, so comparison only works if you can directly tell if something is bigger than something else. If you cannot directly tell, or it doesn't go in the right order for us to make a conclusion, then that's what would drive you to do the limit comparison test. So comparison test is a little easier if you have the kind of the tools that work for that. Okay. Oh, integral test I should have mentioned. You do need to look at this. This can give you the lower and upper bounds for that. Okay, so don't forget about that. All right. So let me just say that I gave you a problem, and you wanted to know whether this series, you know it's a series because it's a sum, is going to converge or diverge. Well, very common thing I told you is for these you're going to compare to something you know how it behaves, which is in general your geometric and your p-series. Okay, so if you kind of just bring this down to the basics, get rid of the plus 1. Okay, so compare it with this. Okay, the question is, do you know what that is? Okay, well, if it's a constant, you could take it out. So the 2, oops, I didn't take it out. The 2 could come out of the summation, and that would leave you 1 over 3 to the n. Well, that's just the same as having 1/3 to the n. And that is clearly just a geometric series with r equal to 1/3, which converges by the geometric series test. Now, I'm not calculating what it converges to, I just know it converges. Okay, so I'm comparing to something that I understand how it behaves. So the next question is, which one of these is bigger? Okay, well, if you're dividing by a larger number, that's going to make this smaller. So it goes like this. Okay, and so basically, our series is smaller than the series that converges. Now, you don't have to write that part. Okay, you're saying that this series is smaller than this series, which converges. And so all you have to say is, therefore, so again, this part you don't have to say, the series converges by the comparison test. Okay, so if you are smaller than a series that converges, you're also going to converge. If you're bigger than a series that diverges, you're also going to diverge. Anything else would not be helpful, and you would have to move on to the limit comparison test. Okay, so my next example is going to be somewhat similar to that. Just going to change it up just a tiny bit. Okay, add a plus 1 there, change it to minus 1. Still going to compare to the same thing. Okay, we've already discussed this one. We know it's geometric. R equals 1/3, converges by geometric series test. Okay, but here we're dividing by a smaller number, so this series is going to be larger. So I'm larger than a series that converges. That tells me nothing. Okay, it could also converge, or it's bigger than it, so it could diverge. So I can't do anything with the comparison test, sometimes called the direct comparison test. Okay, that's what leads me to say, okay, I know something I can compare this to, but I can't just directly compare, so I'm going to go for the limit comparison test. Okay, it's basically the fact that the comparison test failed me. Okay, so if you look at what you're doing there, you're doing the limit as n approaches infinity. It's going to be your series, or the sequence there, compared to, this is the b sub n is going to be whichever you're compared to. Okay, so it's going to be the limit as n approaches infinity of our series, but it's actually just the sequence, the formula for the sequence. And then this is going to be the sequence you're comparing to. Okay, and so for me, I'm going to take the limit as n approaches infinity of my sequence, and then I'm dividing by the one I'm comparing to. Okay, so it's the limit as n approaches infinity of this entire quantity. Okay, and a lot of times, because we know where we're going, we will just go ahead and change it to times and flip. Okay, we're pretty happy here. 2's are canceling, good signs. So we have the limit as n approaches infinity of 3 to the n over 3 to the n minus 1. Okay, the best way to deal with this, to try to figure out what happens as you go towards infinity, is to divide each term by 3 to the n. It's almost like, it's very similar to your leading coefficients, dividing by that greatest power there. So every single term I'm dividing by 3 to the n. Okay, so I would have the limit as n approaches infinity of 1, so this just reduces to 1, over 1, minus 1 over 3 to the n. Okay, and so this I can evaluate now. Okay, as n goes to infinity, this denominator goes to infinity. So overall, the fraction, the denominator is going to infinity. This number overall is going to 0. So it would have 1 over 1 minus 0, which is 1. Okay, so I figured it out. Let me see what the rules are. Okay, turns out if the answer that I get is between 0 and infinity, well, we generally call that positive and finite. So if what you get is positive and finite, then both series behave the same. Okay, so in other words, your series behaves the same as whatever you were comparing to. Well, what you were comparing to was a geometric that converged, and so therefore our series converged by limit comparison test. Okay, so that's the best thing, is if it's positive and finite, they both behave the same. That's what usually happens. There are these other instances that could happen. You could get the limit with 0, and then if what you're comparing to converge, then yours converges as well. Okay, if yours didn't converge, that doesn't help you out at all. Okay, if you get that limit and it's infinity, then if what you were comparing to diverged, then your would diverge as well. Okay, and so those don't come up as often. We're generally looking for positive and finite, but it could. Okay, so we're making it there, getting close. Okay, we've got to do the ratio test and the alternating series test. So the ratio test is good, and again, your nice little sheet here tells you some general principles of when usually one particular test will work. Sometimes more than one test will work, remember that. But I'm going to do the summation from n equals 1 to infinity of 1 over n factorial. And generally speaking, if you see powers, products, or factorials, that's a good time to think about the ratio test. Okay? So here we go. You remember the famous ratio test. You're going to do the n plus first over the first, and take that limit, see if it's less than 1, it converges, greater than 1, it diverges, equals 1, it's inconclusive, and we cry. We cry because if we don't know anything, we're going to have to go try another test. So in general on this, we're going to take the limit as n approaches infinity of the n plus first term over the nth term. Okay, and if it's less than 1, then it'll be converging. Okay, again, greater than 1, we're okay because it diverges. Equals 1, we cry because it is inconclusive. Have to try another test. Okay, and so we're going to try this. The limit, hopefully we won't cry. So we're going to do 1 over n plus 1 factorial, and then you're dividing that by, so just n plus 1 and for all your n's, dividing that by the original. And so all of these are positive, so I'm going to drop the absolute values. You'll have 1 over n plus 1 factorial times the reciprocal. And we want to figure out what that is. So if you'll remember, you can just break down the factorial, whichever one's larger. So it would be n plus 1 times n factorial. So you just keep going down until you reach something you can cancel out with. Ah, beautiful. Okay, I can cancel that out, so I just get the limit as n approaches infinity of 1 over n plus 1. And that just goes to 0, which is less than 1. Woohoo! So this series converges by the ratio test. Okay. Now, this is the test that you're also going to use when they ask you to find the radius of convergence, and the interval of convergence. Okay, so sometimes they'll give you a sequence and just say, find the radius of convergence, find the interval of convergence. When you do that, you're always going to start with the ratio test, and then you might get that the radius of convergence is 0, which means that the series never converges. You might get the radius of convergence is infinity, which means that it works for all real numbers. You might get a radius of convergence of, say, 5, or something like that. And that's the case when you're going to have to test the endpoints to see if they're included or not, and find that interval of convergence. It might be, between 5 and 10 or something like that. Okay, so we'll probably have to do a different review on that, but that ratio test is what you use. When you're testing endpoints, you can use any of your tests. Okay, another thing, time that they ask us to find radius of convergence and interval of convergence is after we have found a Maclaurin or a Taylor series. So we found a series that approximates something, maybe it approximates sine x or e to the x or something like that, and we'd like to know where this is valid. What is the interval of convergence? What could I use this for and be accurate? Okay, so you've made it through all of these. Okay, we only have one left, and that's the alternating series test. But if you remember, we also have to decide then if it's convergent conditionally or absolutely. Okay. So let's work on the alternating series just in general. Okay. And if you look, this is just something that's going to go back and forth between positive and negative. It has two conditions there. The limit as n approaches infinity of the sequence has to be 0. That makes sense, or it would fail by nth term. And also the sequence has to be decreasing. That's what this is referring to. Okay, and if those two things are true, then we can say the alternating series is converging. So not very difficult. Okay, and in fact, if you have an alternating series, then this is the only test I would do if they're not asking me if it's absolute convergence or conditionally convergence. So they're trying to make sure that you have a decreasing sequence. Okay, so when you think about this, you can show it's a decreasing sequence by showing that each term is smaller than the term before it. Okay, so this term is smaller than the term before it. And it's also positive. You notice it's above 0. You can also show the derivative to show it's decreasing. Sometimes we'll just graph it, take a quick look. So it's not really too difficult to find. So let's just do an example. Okay, so pretty decent looking alternating because we see the negative 1 to the n plus 1. Sometimes they use sine and theta and pi to also create an alternating. Okay, so we would try to do this. First, we would just say the limit as n approaches infinity. Notice now we're looking at the sequence without the alternating part. Okay, so just see if without the alternating part, would it go to 0? Okay, because we know that if it does, it also will, if it alternates out of something else that we know. Okay, so this does, in fact, if you compare the degrees, the degree of the denominator is larger. This is going to 0, or you can L'Hopital it, whatever you like. Okay, and then you can just show that it's decreasing. You could use your graphing calculator. You could say something like, you think that when you put in the n plus first term, it's going to be less than or equal to just putting in the regular term. That's not really useful unless you can just like directly compare and tell that. But if you want, you could show a quick little graph, or you could take a derivative. Okay, so basic methods. But basically, if you can show these two things are true, then you can say that this converges by the alternating series test. Pretty easy. Okay, you don't know about absolute or conditionally, but if they don't ask you, they just want to know converges, go to this. It's quick and it's easy. Okay, a couple of other things you need to remember. Notice that it's telling you here, it's reminding you that if you sum, just say the first 50 terms, okay, then you know that your error for summing the first 50 terms will be less than whatever the 51st term is. Okay, so all you have to do to get an estimate of the error, you know it's going to be less error than the next term. Okay, so the absolute value of the error is less than or equal to the next term in the sequence. So if it was the remainder for the first n term, sum is less than or equal to u sub n plus 1. Also, the sum to infinity lies between any two successive terms. Okay, so if you find the sum of the first 50 terms and you find the sum of the first 51 terms, then you know that the real sum is going to be in between them. Okay, so we can narrow down and get, well, we can't find the exact sum, we can at least narrow it down. Okay, the very last thing that I need to tell you about is if they ask you to find out if it's absolutely convergent or conditionally convergent. Okay, so again, if they ask absolutely or conditionally. Okay, so if they just ask you, they just give you an alternating series and they want to know does it converge or diverge, just go for the alternating series test. It's very quick. But if you have to know the type of convergence, then you're going to need to go through a few steps. Okay, the first step that I would do is the same thing I would do on anything that I was looking at, nth term divergence test. Okay, just see, is the sequence itself going to 0 or not? Okay, because if it's not going to 0, the thing diverges, you don't have to worry about it. Okay, next I would test to see if it's absolutely convergent. Okay, what that means is see if the series would converge if it was all positive, if it didn't go back and forth. If it will converge when it's all positive, in other words, you can sum that, then if every other term is negative, that's going to be even smaller. So if it converges when it's not alternating, then it's going to converge also when it's alternating, and we call that absolute convergence. Okay, meaning that it converges whether it alternates or not. Okay, and for that, you can use any of the tests. If that fails, in other words, if when it's all positive it doesn't converge, then you have to go to the alternating series test. Because if it's all positive, it could diverge, but going back and forth, positive, negative, you might be okay. Okay, and really our best example of that would be the harmonic series. The harmonic series diverges, but the alternating harmonic series converges. Okay, so that's one of our classic examples. So we're just going to take one final example, summation from 1 to infinity, with a nice alternating series. Okay, and so the first thing I would do there, asking me, is it absolutely convergent, conditionally convergent, or divergent? Okay, so the very first thing I'm going to do is just make sure this guy doesn't diverge. Okay, and maybe I'm not sure how that behaves, so I'm just going to graph it really quickly. I'm going to graph the sine of 1 over x. Okay, and I want to see what happens as it goes towards infinity. It does appear to be going towards 0. Okay, so I'm pretty satisfied with that. Okay, and if I got anything besides 0, I'd be like, this is divergent, I am done. Okay, but I didn't, so I have to keep working. Okay, so what I'm going to do now is see if the summation of the absolute value of this, see if it's convergent. Okay, so basically once I get rid of the alternating, I can use any of the tests that I know, all the other ones that we talked about. So I want to see if this is convergent. If this is convergent, then we have a rule that says, a theorem that says that if the summation of the absolute value of a series is convergent, that implies that the original series, that is your alternating one, is also convergent, and that would be called absolute convergence. But if the absolute value one doesn't converge, but it does if it alternates. That's what conditionally convergent is. Okay, so absolute convergence means that it converges whether it alternates or not. Okay, so what I'm going to do is try to figure out what this does. Okay, so instead of looking at the alternating, we're going to look at the positive. Okay, and I'm going to do a limit comparison with the summation from n equals 1 to infinity of 1 over n. Okay, so this is either p series with p equal to 1, or you can look at it as your harmonic series, but this one definitely diverges by, I'm going to just say harmonic series, or p series test, p equal to 1. Okay, and so when I do my limit comparison test, I'm going to take the limit as n approaches infinity of my function over the function I'm comparing with. Okay, and we already graphed this a second ago. You can kind of see that it's heading towards 0 there. Okay. And we know that this guy, as n goes to infinity, this goes to 0. So we get a good old 0 over 0, which tells me that I can apply L'Hopital's. So I can do the limit as n approaches infinity, derivative of the top over the derivative of the bottom. Okay, so the derivative of sine is cosine, so cosine of 1 over n, chain rule, times the derivative of the inside. Okay, so this, little guy right there, is n to the negative 1. So if I take the derivative of it, it's negative 1 n to the negative 2. And then this is also n to the negative 1. So derivative would be negative 1 n to the negative 2. These guys cancel. Okay, so now I have the limit as n approaches infinity of cosine of 1 over n. And let's just take a look at it. So cosine of x. And this guy is flattening out at 1. Okay, kind of like this goes to 0 and cosine of 0 is 1. Okay, and so this guy is 1, which is positive and finite, which means both behave the same, which in this case means that this series diverges by limit comparison. Okay, therefore this does not converge absolutely. So if the absolute value of it converges, then also the alternating one converges, which means it converges whether it alternates or not, which is called absolute convergence. Okay? And so since that doesn't happen, the last thing is you got to use the alternating series test. Okay, see, okay, if it's all positive, it's definitely going to diverge, it's going to explode. So I'm going to try the alternating series test. Maybe if every other term is negative and I add it up, maybe it's got some kind of a bound. Okay, so the two things to check, like we did before, we have the limit as n approaches infinity. We have already done that up there. Okay, then you just want to see, is it a decreasing function, which would look like this. For n greater than or equal to 1. Now, I just don't particularly know that. I think we graphed that a minute ago. It is a decreasing, you might even do a little sketch on your paper, just showing, goes crazy in the middle, but then it's decreasing. Okay, so this is a decreasing function. Which is the other thing that we have to show. Okay, so I'm showing it there. Didn't really algebraically prove anything. Therefore, this converges conditionally for n greater than 1. Okay, so again, we could have just shown right from the start that it converged. We just wouldn't have been able to say that we knew for sure it wasn't absolute convergence without having checked that. So those are your basic series tests. If you look here at it overall, you've got to memorize it. Sometimes what confuses people is the less than 1 and the greater than 1. So if you kind of remember, this is on your formula sheet anyways. for under algebra for knowing that the absolute value of the common ratio has to be less than 1. It's also common sense. Your numbers have to be getting smaller, and that's what the common ratio is showing. So that one's a less than 1, and this one is less than 1. Okay, on the ratio test. So the only one that kind of bucks the curve is this p greater than 1, being the condition for convergence. But if you think about a p-test in general, okay, if you think about what's going to happen as the limit as n approaches infinity of, say, 1 over n squared, that's going to go to 0. But if all of a sudden you make this something negative, 1 over n to the negative 2, well, that's just the limit as n approaches infinity of n squared, which is going to go to infinity. Okay, so all these numbers that are smaller than 1 are actually going to flip and make these big numbers, so it makes sense that this is going to diverge. Also, you know the 1 is your harmonic, which we talked about for a really long time, so no problem there, 1's going to diverge. Okay, so that's really the only one when you're trying to keep your rules straight just from a memory point of view, okay, that these less than 1 normally means convergence, but not for your p-series. Okay, so again, look at the rules down here, kind of tells you when a particular test might be more useful, and again, sometimes more than one test will work. Roger, Dodger.